This conference will now be recorded.
Hello everyone. So this problem we have already started in last class, but we have not finished it because it has total 3 parts. And we have already seen that how we can find out the oxidation state of manganese in each reduction product. So here we have already seen what will be the oxidation state of manganese in each reduction product. And if we already know what will be the fate of manganese when it is acidic medium, then neutral medium and alkaline medium. But in case if you cannot remember it, then you have to construct 3 equation, that is in acid medium Mn plus 7 accepting N1 number of electrons, and it is converted to, that is after accepting this number of electron, it is converted to A plus state. Similarly, when it is neutral medium, it is accepting N2 number of electrons and it is converted to some lower state, which is B plus. So N2 will be equal to 7 minus B. So this is one equation. Then we are getting another equation, and alkaline medium third equation. Now here we will do the calculation in terms of milli equivalent. Milli equivalent of the reducing agent, that will also be equal to milli equivalent of MnO4, whether it is acidic, neutral or alkaline. Now how we can get milli equivalent? Simply multiply the volume in ml, which is 20 ml when it is acid, 33.3 ml when it is neutral and 100 ml when it is alkaline medium. So multiply all these volume in ml with molarity, but we also have to multiply N1 when it is acid medium, N2 when it is neutral and N3 when it is alkaline. Now why we are doing so? Because the calculation is not millimoles. If it is millimoles, simply multiply molarity with volume in ml, but here it is milli equivalent. So that is why we also have to multiply how many number of electrons are actually involved. So now we can say that 20 N1 is equal to 33.3 N2, that is equal to 100 N3. So if we simplify it, it will reduce to this type of relation among N1, N2, N3. Now N1, N2, N3, it will always be integers because this is nothing but number of electron. It is always a whole number, right? It cannot be fraction. So that is why N1, if it is equal to 1.66 N2, that means N1, if we consider 5, N2 3, that means when you multiply with 1.66, you get 5. That means this quantity is 5. And when N3 you consider 1, obviously this quantity is also 5. That means all these are 5. And that is possible only when you consider these values of N1, N2 and N3. Now once we know the value of N1, N2 and N3, now we have to use all these equation so that we can get the value of A, B and C. Because A, B, C, these are the oxidation state of manganese in different medium: acidic, neutral, alkaline. So we will put all these values of N1, N2, N3. So when it is acidic medium, it will be +2. When it is neutral medium, it will be +4. When it is alkaline medium, it is +6. So now we have already obtained the answer of the first question, that is the oxidation state of manganese in different media: acidic, neutral and alkaline. Now come to the second part. The second part is asking, give the balanced equation for all the 3 half reactions. Now how to balance half reaction, that we have already discussed. So see, these are the balanced equation. Only one I am discussing. Just take the first one. Here in acidic medium, MnO4 minus from +7 state, now it is converted to +2 state. Now we have total 4 oxygen in the left hand side. Now we will add 4 water molecules because we have to make oxygen number equal both sides. Now when you have added 4 water molecules, you have also added 8 hydrogen. So left hand side also 8 hydrogen must be there. So that is why we are adding H plus. And it is possible because the medium is acidic. Suppose the medium is neutral, in that case you cannot add H plus. Fine. Next what we will do, we will see whether the charge is balanced or not. Left hand side there is single negative charge over MnO4, single negative charge, and 8H plus. That means total positive charge will be 7 positive charge. And in the right hand side you have only 2 positive charge. That means if you add 5 electron, then only both sides will be having same positive charge. Now both sides there is +2 charge. So in this way we can balance all the equations. So this is the answer for the second question. This is for the first question. And the third question is asking, look at the third question. It is asking that find out the volume of 1 molar potassium dichromate. Now potassium dichromate is another oxidizing agent just like KMnO4. We have to find 1 molar K2Cr2O7 consumed. What is the corresponding volume? If the reducing agent that we are using means, in case of KMnO4, the reducing agent that we have used, suppose we are using the same reducing agent when oxidizing agent is K2Cr2O7. So keeping the volume of the reducing agent same, if we are doing the titration in acidic medium, because K2Cr2O7 also works at acidic medium. Fine. So we have kept volume of the reducing agent same, the reducing agent itself is same, medium is acidic, concentration molarity of K2Cr2O7 that is also 1 molar, just like KMnO4, because here also it is 1 molar. So we have to find the volume. Now for the third part, first we will write the balanced equation for K2Cr2O7 oxidation in acidic medium. We know that acidic medium Cr2O7 2 minus, which is having +6 oxidation state. Now it will be reduced to +3 oxidation state. There are total 2 chromium atoms, so that is why it will be, we have to multiply it with 2. Next, there is 7 oxygen atom in the anion, so we are adding 7 water molecules. Now when you have added 7 water molecules, there are 14 H you have added, so that is why now we are adding 14 H in the left hand side. The next step will be charge balance. We have 2 negative charge here, 14 positive charge, that means 12 positive charge. But in the right hand side we have 3 into 2, 6 positive charge. So left hand side 12 positive charge, right hand side 6 positive charge. If we want to balance it both sides, we have to add 6 electron. So that is why the electron number is 6. Now this number is very important. Why it is so? Because now we will use the normality. So when you are converting molarity to normality, that is 1 molar K2Cr2O7, when you are converting to normality, you have to multiply it with the corresponding electrons that are involved. Next is, now same thing that we have already done in case of KMnO4. We will do the equation in terms of milli equivalent. Now milli equivalent means volume in ml that will be multiplied by the normality. Volume in ml is 20 ml 5 normal KMnO4. Remember, when it is acidic medium, what we have used? We have used 20 ml KMnO4, right? And what is the that is milli equivalent of KMnO4 is acid. Remember, this is the milli equivalent of KMnO4 acid, and N1 is 5. That means it is 1 into 5 into 20. So same thing we have done here. So when it is milli equivalent of reducing agent, that must be equal to milli equivalent of KMnO4, because we are using the same reducing agent, and that is also equal to milli equivalent of K2Cr2O7. Now focus on these two part only. Milli equivalent of KMnO4 will be 20 ml 5 normal, because that is the volume of KMnO4 in acidic medium. But we do not know what is the volume of K2Cr2O7, but we know what is the normality. So that is why we have written VML 6 normal. So 20 ml 5 normal KMnO4 equivalent to, this is equivalent side, VML 6 normal K2Cr2O7. So if we want to know what is the volume of V, now it will be 20 multiplied by 5 divided by 6, and the answer is 16.66 M. This is answer for the third part. So is there any doubt in any of this part? Then I will repeat it once again. Is this clear? So that is all about D block. Next we will start the other block, which is A block. So before going to A block elements, here we have the periodic table once again, and there is a reason behind that. Is D block is this part, right? And we have focused mainly on the first transition series, that is starting from scandium up to Zn. Group number is starting from 3 up to 12. Okay, this is second transition series, this is third transition series, but mostly we have focused on the first transition series. Now if you look at this part here, after barium in S block, when we are entering D block, then the element is La, lanthanum. Okay, but lanthanum, though here it is the next element after Ba, but after La, the next element is not HF, because though it is a single place, but here basically 15 elements are residing simultaneously. So all these 15 elements starting from lanthanum up to lutetium, all these are placed in the same box. Okay, that means all these elements, they are having same period and same group, and this series is known as 4f. Why it is 4f? Because here electrons are gradually filling in the 4f orbital. Just you have seen in case of D block, electrons are gradually filling in the D orbital, and that is why they are under D block. But now it is 4f, orbital is filling gradually, so that is why they are under F block. But F block is mentioned under the periodic table. It is not directly placed in the periodic table. But why it is so? Because if you write La starting from La up to Lu, all this in this single position, then the periodic table, that will be very wide. So the reason behind why we have placed this 4f block, and also there is 5f block, which is for the next period, there is specific reason behind that. So what is the reason? The reason is, if we put lanthanides and actinides in the periodic table, just like transition metals we have seen, we have just finished D block, then the table will be very wide. So that is the reason that practically it will be difficult to handle this periodic table, because it will be very wide. So that is the reason that the two rows of elements present at the bottom of the periodic table, and they are known as 4f series or lanthanoids. Lanthanide, the name is given, it is depending on the first member, and 5f series or actinoids, that is also based on the name of the first member, and they are also known as inner transition elements. So see, if you put all these in the directly in the periodic table, the periodic table, it will look like this. So here what we have done, this is actually imaginary periodic table, this is not the actual periodic table. Here after barium we have placed La, then all these 14 elements up to lutetium, and then we are starting hafnium. Then the periodic table is so large because this part is S block, after that this part is totally F block, and then D block, and after that this is not even the end, it is still continued, and after that there will be P block, which is not even possible to write in the same place. So that is why it will be very wide, which is really difficult to handle. So that is why all these elements together, all these elements together, they are placed in the same box. Okay, so that means all these 15 elements, they will have same period as well as same group. Fine. So is there any doubt that why these 4a block, 5a block, they are not directly placed in the periodic table, but they are mentioned just below the periodic table separately? Okay. So in this table we have only the F block elements. 4a block because here electrons are gradually filling in the 4f, and 5a block electrons are gradually filling in the 5f. Okay. So before cerium there is La having atomic number 57, And here we have Ac, actinium, which is having atomic number 89. So starting from 57 up to 71. Fine. If you do the counting starting from La up to Lu, it will be 15 elements. Okay. But if you do the counting starting from cerium, it will be 14 elements. Now, it is easy to understand that we know that F orbital maximum capacity of electron is 40 because there are total 7 atomic orbitals. And in each orbital, maximum 2 electrons can be placed. So 7 into 2, 14 electrons, that is the capacity. So gradually, when electrons will be filled, obviously 14 elements possibility is there. But for the first one, here actually it is 4F0. So if you start from 4F0, then 1, 2, 3, 4, ultimately up to when you will reach lutetium or lawrencium, that is 103 atomic number, it will be 15. So 1, 2, 14, and then if you consider this 0, then it will be 15. Fine. So in this element, the last electron is entering pre-penultimate shell. Now try to understand the meaning of pre-penultimate shell. Valence shell is, this is the general electronic configuration. Ns is valence shell. But when it is n-1d, that is actually penultimate shell. That is the orbital which is just before Ns. N-2f, that is pre-penultimate because it is coming before n-1d. So that is why the name is pre-penultimate. Now here we will have F electron starting from 0 up to 14. So that is why 15 elements. And D electron, 2 possibilities are there. Sometimes the configuration is D0. Sometimes it is D1. And Ns it is always 2. Now n-2f orbitals, they are obviously inert to pre-penultimate or anti-penultimate shell. So that is the reason they are called inert transition element. So remember, this pre-penultimate shell, that is also having another term which is also known as anti-penultimate, and as they are very placed in very inert position, so that is why the name is inert transition elements. Here the differentiating electron in transition elements may enter either 4f and 5f. Sorry, it is inert transition elements. So this electron, this n-2, it may be 4 or it may be 5. So when it is 4, then this will be 5 and Ns will be 6s. But when it is 5f orbital, then this part will be 6 and this will be 7s. So the differentiating electron, it may enter either 4f or 5, based on which we have 2 different series, lanthanides and actinides. Fine. So in lanthanides, the differentiating electron will enter 4f orbital, and the name of these lanthanides, it is because they come immediately after lanthanum. So lanthanum is the first member where F0 electron present. So that is the reason, based on the name of the first member, they are called, that is in general they are called lanthanides, and it is denoted by Ln. Remember, it is denoted by Ln, short form. So see here we have the general electronic configuration. After xenon, which is noble gas configuration, we have 4f0 to 14, then 5d0 to 1. So you can find similarity with this electronic configuration, and 6s2. So here n value is 6. Now come to actinides. Here everything is same, but now we will have 5s orbitals which will be gradually filling with electrons, and these are starting from thorium atomic number 90 up to lawrencium 103. These elements come immediately after actinium, which is having atomic number 89, and that is why in general they are called actinides. In short form, it is written as AN. So for actinides, after Rn configuration, it will be 5f 1 to 14. Now see here, little difference you can see. In case of 4f, it is starting from 0 to 14, but here it is 1 to 14. So one electron that must be in other orbital. Here it is 5d 0 or 1, but here it may be 6d 0 to 2. That means it may be 6d 0, 6d1 or 6d2. Three possibilities are there. But outermost orbital, that is always 7s2. So here n value is 6. So n minus 1 is n value 7, n minus 1 6, n minus 2 is 5, and here n is 6, n minus 1 is 5, n minus 2 is 4. So any doubt in the electronic configuration of these two series? So first we will start with lanthanides. After that we will see actinides. Here we have electronic configuration of lanthanides. Okay. So here the symbols for lanthanum La, and then up to lutetium Lu, it is Gt. Now look at the configuration for Ln. Ln is the general term that I have already mentioned. So it will be, for the first one, there is no F electron. It is basically 4f0. Okay. So it is not written. You can also write. Both are actually same. 6s2, 5d1. So 6s2, that will always be present. The next element, this is also 6s2, but now the next electron that is entering 4f. So that is, it is 4f1. Now after cerium, when we have praseodymium, Br, now we do not have any d electron. Remember, for lanthanides, it may be 5d0 or it may be 5d1. So in this case, it is 5d0. And the next element, next electron, that is actually entering F. But why it is 4f1? It should be 4f2. It is for now, but it is not 4f2. It is 4f3. Why? Because the electron from D, that is also now transferred to F. So sometimes there is some difference in, it is not gradual always. And why it is so? Because it depends on so many things. The net energy, it actually depends on what is the net energy. So maybe that this configuration, it will be lower energy, and it will be, that is, if suppose the configuration is 4f2, 6s2, 5d1, that maybe it is having higher energy. So that is why it is mentioned in this way. It is difficult to mention any specific reason behind it. Okay, so there is no other way, but we have to remember it. Fine. After 4f3, there is 4f4. Again, it is 5d0, 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 5d0. Now, when we have reached gadolinium, now see, the next electron is entering 5d, not 4f. So that is why it is 4f7 for europium. For GD also it is 4f7. Now suppose the electron is entering 4f, it will be 4f8. But 4f7 is stable half-fill configuration, so that is why this configuration is preferred. Next electron, again this D electron is entering F. Also the added electron that is entering F. So that is why after 4f7 directly it is 4f9. Then 10, 11, 12, 13, 14. Now when you have reached lutetium, the next electron is entering 5d1, and the reason is same, because 4f14 is the fully filled configuration and it is stable configuration. Okay. Now if we see the electronic configuration for Ln, there are some discrepancy you can see. But if you have the oxidation state 3+, and then you are writing the electronic configuration, now you can see there is some gradual change in the electronic configuration. It is smooth change. Okay. So 3 electrons are removed. That means 6s2 electron, 5d electron removed. Now it is 4f0, it is 4f1, and it is moving gradually up to 4f4. So this is very easy to understand. Next we will see the radius of this cation oxidation state 3+, and the values are in picometer unit. See here, the values are gradually decreasing. That is fine, but the decrease is not very large. I am trying to say that the difference in the decrease. So 116, 114, that means difference is only 2. Then here difference is 1. This is 2. So either 2 or 1. This is the difference. Okay, and sometimes it is almost same. So that is why, though it is decreasing, that is, as you are moving from left hand side to right hand side, the sizes are gradually decreasing, but the difference, that is, it is not very drastic decrease. It is very smooth and slow decrease. Okay, any doubt? In the electronic configuration, all these are atomic number, that is this Z value. Next, we will see atomic sizes of lanthanides and ionic sizes of lanthanides. So when it is atomic size, that means it is neutral atom, no charge is there, but when it is ion, we will consider the 3+ oxidation state. We know that all lanthanides are placed in the same group and same period, right? Just after barium. But atomic and ionic radii of lanthanides, they decrease with an increase in atomic number. That means from left hand side to right hand side, there is smooth decrease. Here this dotted line, that is metallic radius, which you can also say atomic radius. And the crossed line, that is for Ln3+ state. So this is the ionic radius. So this line is ionic radius and this is atomic radius. Now it is very easy to understand. See, radius is given in picometer unit in y-axis, and x-axis we have all these elements with increasing atomic number. And here the values are near 190 picometer, but as it is ionic radius because it is scattered. So compared to Ln, when it is compared to Ln, when it is Ln3+, that means we have removed 3 electrons. So the size of Ln3+, obviously in general it will be very lesser than Ln. Okay, so that is also clear from the picture because it is around 190 picometer, but all these values are in the range of 110 to 130. But in both cases there is decrease. So when you consider ionic radius, the decrease is very smooth, right? But when it is atomic radius, two discrepancy we can see. And these two discrepancy, it is at europium, another one is at ytterbium. Now look at the configuration of ytterbium. 4f14 6s2, europium 4f7 6s2. That means if you remove these 2 electron, it will achieve stable half-filled configuration 4f7. And from ytterbium, if you remove 2 electron, it will achieve 4f14 stable configuration, right? Now the question is why the atomic radii of these two elements, EU and YB, they are much higher than expected, because suddenly there is increase, right, at these 2 points. Now this is because of the fact that these two elements, they can donate only 2 electrons in the metallic bonding. They will donate only the 2 electron that is present in 6s, because they will not break this configuration 4f14 and 4f7, because that is very stable configuration. So they are contributing only 2 electrons in the metallic bonding, and as a result metallic bonding will be weak. And as metallic bonding is weak, the atomic radius, that will be very high. So that is the reason there is sudden increase at these 2 elements. But for other elements, not just these 2 electron, but other that is electron from D as well as F may also be contributed, and that is the reason now metallic bonding will be very strong. And when metallic bonding is very strong, atomic radius, that will be lower. Okay, so remember, for ionic radius, there is smooth decrease, but when it is atomic radius or metallic radius, this is also decreased, but there is discrepancy at europium and ytterbium. Okay, except these two, there is smooth decrease. And the smooth decrease, that is gradual decrease, that is known as lanthanide contraction. Now this term is very, very important because this lanthanide contraction, this phenomena is responsible for so many other factors. Okay, and we will come to that one by one. So that will be discussed under the consequences of lanthanide contraction. Okay. Now, why this lanthanide contraction occurs? That is the question. Okay. For that, here we have this picture. See, it is nucleus which is carrying all these positive charge proton, and this is inner f orbital. So all these electrons are inner electrons, and these electrons in the blue line, they are outer electrons. So inner f orbital and outer electron means s. It is 6s. So order of shielding effect for different orbitals, it is already known that S is having maximum shielding effect, but F is having very poor shielding effect. Okay, that means these electrons, inner F electrons, they cannot shield the outermost electrons from the positive charge very effectively. And as a result, what happens? The attraction between the nucleus and the outermost electron, this attraction between this positive charge and outermost electron, that becomes very strong. As a result, the size will shrink as we move from left hand side to right hand side, that is with increase in atomic number. Okay, so this is the reason why gradually as we move from left to right, size is decreasing. But you can also say that there is another factor, which is repulsion between outermost electron and the inner electron, and because of this repulsion, the size may also increase. So because of this reason, size should increase as the number of electrons are increasing from left hand side to right hand side. But the other factor, that the shielding effect of f orbital is very poor, and that is the reason the distance between the outermost electron and nucleus decreases. So this second factor is overcoming the first factor, and the net result is that as we are moving from left to right, the size is decreasing. So in case of lanthanides, electrons are successively filled in 4s subshell, which is the pre-penultimate shell. With increase in atomic number, the nuclear force of attraction increases. Why? Because when atomic number is increasing, that means electron number is increasing as well as proton number increasing. So proton number increasing means what? These positive charge values, that will also increase. Now the outermost shell is 6 shell, that is 6s, which is shielded by these added electrons, because the added, that is the electrons that are added as electron atomic number is increasing, they will be added in the inner f orbital. But outermost orbital, that is 6s electron, that is fixed. Okay, so there should be some shielding, but this shielding is very poor. Fine. The shape of f orbitals are such that electron cloud is diffused, and also penetration of f orbital towards nucleus is minimum, and that is why there is poor shielding effect. And as they cannot shield properly the outermost electrons, there will be increase in attractive force of nucleus by this, that is on this outermost electron. So the increase in attractive force of nucleus, that factor will be winning. It cannot be compensated by the shielding effect, because this effect is very, very poor. Okay, so is it clear why lanthanide contraction actually happens? The main reason is increasing, that is the shielding effect of f orbital, that is very poor. Okay, any doubt? Now, consequences of lanthanide contraction. This is very important part. So there are different consequences actually. We will come to that one by one. At the first point, we have similar properties of second and third transition series. So look at this box. Here we have first transition series, second transition series, third transition series. Okay. Now the values that you are seeing here, these are basically densities. Scandium, ytterbium, La. Now between La and HF, there is 14 elements present. Okay. But if you consider the group number 3, this is group number 3. So what are the elements we have? Scandium, ytterbium, La. Now as we move down, sorry, these are not densities, these are basically size. Okay. As we move down, obviously the size will increase because number of periods are increasing, there will be extra added valence shell. So there is smooth increase. See, 1.62, then 1.8, then 1.7. But when you move to group number 4, 5, 6, etc., etc., now see, when you move from first transition series to second, there is normal increase. But when you are moving from second to third, now these two values are almost same. See, all these values are very close. But that is not for the first group, because in first group, these 14 elements, they are not yet present. Only La is there. But when you are moving from 3 to 4, 5, 6, 7, 8, now already these 14 elements are included. So that means lanthanide contraction effect is already added. And as a result, from Zr to HF, from NB to TA, when you are moving, there is no expected increase. And the reason is lanthanide contraction. So we know lanthanide, because of lanthanide contraction, there is decrease in the size from the expected value. And that effect will also continue. Even the lanthanide series is complete, but still it will be continued in all these values. So between La and HF, we know there are 14 elements and all these are lanthanides. So in there is already, we have seen in the last slide, that decrease in both atomic radius as well as ionic radius. Fine. Now here hafnium, that is after zirconium, the value is much smaller than expected, right? Now if you look at this graph, which is basically having atomic radii in nanometer in the y-axis, and this is actually in picometer values. So that is why it is 1, then point, and here it is point, and then the value. So this black line, this is for first transition series, the blue line for second, the purple line is for the third. Now the blue line and the purple line, they are completely overlapping to each other, right? That means the size of this second series and third series sizes are almost same, except the first. That is, see here, when you are moving from scandium to ytterbium to La, there is normal increase. But after that, when it is group number 4, then group number V, that is vanadium, niobium, tantalum, group number 5. Now see, there is gap between these two, but these two are same. Okay. So this is because of the increase in atomic radius due to addition of one shell from Zr to HF. And that effect is compensated because that is the expected observation, that when you are moving down the group, there obviously should be increase in size. But that effect is compensated by the lanthanide contraction. And similar is the case for all these pairs: molybdenum, tungsten, technetium, rhenium, ruthenium, osmium, rhodium, iridium, PD, PT, palladium, platinum, silver, gold, cadmium, mercury. Fine. So because of this similarity in size, what happens? Their chemical properties are also very more or less same. Because size effect, it has the size value that has direct effect on the chemical properties. So as the sizes are almost same, so chemical properties will also be very close to each other. And that is the reason all these are called chemical twins. That is, all these pairs are called chemical twins. Fine. So this is the first consequence of lanthanide contraction. So this is the effect, and lanthanide contraction is the cause. Okay. Second point. This is first point. Separation of lanthanides. So suppose there is no lanthanide contraction and all these elements are having same size because they are placed in the same group, same period. So suppose they are all having same size. Then what will be the problem? When you will try to separate the mixture of lanthanides, you will not be able to do so. Because if there is no difference in size, it is difficult to separate them. So without lanthanide contraction, all of these elements would have same size. And because of this, it will be very difficult to separate them. But as there is lanthanide contraction, even if the difference between them is very small, okay, but still there is some difference. So these properties, as they are slightly varying, that is, the sizes are slightly changed. So this variation in the properties that will be utilized to separate them. Because separation of lanthanides, suppose normally it is done in column chromatography. So in column chromatography, size is very important. Okay. So if all these are having same size, they will be attached to the column bed to the same extent. So it will be, they will be eluted simultaneously. But if there is difference in size, their interaction with the column bed will be different, and as a result, they will be coming out from the column one by one, not together. Then the third point, basic strength of hydroxide. That means here we are talking about LNOH whole 3. Ln is the general term. Ln is any lanthanide. All of these lanthanide, when they are in +3 oxidation state, they can form this type of hydroxide. That means if it is dissociating, it will be forming Ln3 plus and 3HO minus. Okay. So this type of dissociation, when it is very good, then HO minus concentration is high, and HO minus concentration is high means basicity is also very good. Okay. Now we know that ionic size of Ln3 plus ions decreases from La to Lu because of lanthanide contraction. So what happens? Now the covalent character between Ln and O bond in this LNOH whole 3, because LNOH whole 3, suppose the OH is attached in this way, right? Now this bond between Ln and O, whether it is ionic or covalent, that also depends on the size of Ln3+. So if the size of Ln3+, it is very, very small, that means charge density is very high. Because if it is, that is for different elements, size is different, right? But charge is same. Now charge density means what? Charge divided by volume. So when size is different, volume will also change. Suppose size is very small. When you are moving from La to Lu, for Lu the size is very small, that means volume is also very small. But charge is always 3+. That means the denominator is decreasing. So as a result, what will happen? This ratio, that will be very high. So as you are moving from La to Lu, charge density is increasing, and as a result, covalent character will also increase. And this is according to Fagan's rule, that when charge density of the metal ion, that is the cation, is increasing, covalent character increases. Now what is the meaning of covalent character increases? When covalent character increases, that means the dissociation of this LNOH whole 3 to this cation and anion, this type of dissociation will be reduced. because this is the property of ionic compound. But suppose if LNOH whole 3 is very, very covalent in nature, this type of dissociation will not be very high. That means in the medium, HO minus concentration will decrease. And HO minus concentration decrease means what? Basicity will decrease. So it becomes difficult for the hydroxide to donate HO minus ion when covalent character is very high. As a result, basic strength goes on decreasing from left hand side to right hand side. So this is a right hand side, extreme right hand side. We have notation. LA is extreme left hand side. So what is the final conclusion? As we are moving, that is in the 4F series, you are moving from left hand side to right hand side, basic strength will decrease. So that is the reason LaOH whole 3, which is the first hydroxide, that is the first member, it's hydroxide. It is having maximum basicity, but the last member is hydroxide, that will have minimum basicity. Okay. So this is the how basic strength is changing, and the reason behind it is lanthanide contraction. So is there any doubt in these 2 points? Should I repeat? Number 4, high densities of post-lanthanide elements. Post-lanthanide elements means the elements that are coming after lanthanides. Okay. Now remember the first point. I'm talking about this point. This in this slide, what we have discussed, that for second series, and third series, the sizes are almost same. Now, when sizes are almost same, that means the volume is almost same. So for all these chemical twins, niobium, tantalum, molybdenum, tungsten, ruthenium, osmium, all these pair, they will have same volume. Okay, but when you are moving from Nb to Ta, that is you are moving from Nb to Ta, then molybdenum to tungsten. Basically, mass of tungsten is much higher than molybdenum, right? Because it is in the next period, and obviously atomic number is high. So volume is same, but mass is very high. So what I'm trying to say, when you are thinking about density, density is mass by volume. Density, mass by volume. Now M is increasing, but V is fixed. That means the denominator is unchanged, but the numerator is increasing. So this ratio will obviously increase. That means density will be very high for the post-lanthanide elements. And what are the post-lanthanide elements? All these elements in the third series, they are post-lanthanide elements. These elements are not post-lanthanides, okay? But the last series, they are post-lanthanides. Now come to this slide. High densities of post-lanthanide elements. When we move from Zr to HF, the atomic weight increases by about 2 times, because you are now moving to the next period. So obviously the mass will high. But remember, HF is just below zirconium. So their volume same, but mass is already, it is double. But because of this lanthanide contraction, atomic radius remains almost same. That means volume is also same. So that is the reason now density of HF, it is much higher, almost twice, because the denominator is not changing, but the numerator is now double. So the ratio will be double as compared to zeta. And similar is the case with all the post-lanthanide elements. So if you consider any chemical twins, you will see the same observation. Now look at the values of density. All these are density. 6.4, this is 4.5. So when you are moving from first to second, there is increase, but not so drastic increase. But now see, 4.5, 6.4, it is not almost double, but when you are moving from second to third, now it is 11.4, which is almost the double the value of zeta, right? But for the first group, that is, I'm talking about these 3 elements, you will not see this difference. Then niobium 8.4, Tantalum, it is almost double. This is 10, it is almost 20. 11, it is almost 20. Okay, so in this way you can see there is drastic increase in density. After this point, number 5th point, poor complex formation tendency. Complex formation tendency we have seen in case of D block elements. This is very that is common. Okay, but in case of lanthanides, here complex formation tendency compared to D block elements, it is much less. So although lanthanides ions, they have high charge. So when there is high charge, we can expect that complex formation tendency should be good. But though the charge is high, but the problem is the size of their ions are very large. So compared to D block, now we have already reached 6th period, right? So obviously the size is very high. So charge by size, this ratio will be very small because denominator is very small. Sorry, denominator is very large. So because of this small charge density, they will have poor tendency to form complexes. Okay. Now though we are saying that poor complex form tendency, but some examples are obviously there. So there are some specific ligands with which they can form compound. They mainly form complexes with chelating agents. Chelating agent means more than one donating site must be present. So beta diketone is like this. It is also known as 1,3-diketone because if this is alpha position with respect to this keto group, then sorry, it is not beta keto. Yes, this is 1,3-diketone. Why it is beta keto? Because this is alpha position with respect to carbonyl group. This is alpha position, this is beta position. So in beta position there is another keto group, so that is why it is beta diketone. Then EDTA, ethylene diamine tetraacetic acid, 2,2' dipyridine. It is 2-pyridine if connected together. So see, this is bidentate ligand, 2 donating site is there. Then beta hydroxyquinoline. So all these ligands you will see more than one donating site is there. That means they are chelating ligand. They will form some ring structure after binding with metal. So complex formation tendency and stability, it will increase from La to Lu, and the reason is charge density increases. So that is the first 3 points. They are saying that poor complex formation tendency, but we are discussing consequence of lanthanide contraction. So what is the consequence? So though in general their complex formation tendency is poor, but if it is asked what is the trend as we are moving from La to Lu, now the trend is complex formation tendency and as well as stability both will increase because charge density increases. Why charge density increases? Because charge density is charge by volume. It is density, right? So when we say normal density, it is mass by volume. So when it is charge density, it is charge by volume. So volume gradually decreases left hand side to right hand side, but charge is fixed. So volume decreases means charge density will increase, and that is the reason when you are moving from La to Lu, the complex formation tendency increases. Okay, so these 2 points are clear. Now we will see general characteristic of lanthanide elements. All of these lanthanoids, they are actually metallic in nature. They are silvery white soft metals, and when they are in open air, they tarnish very rapidly, and it is because of the reaction with oxygen. There is a formation of oxide layer, so that is why they tarnish rapidly in air. Hardness of this metal increases when there is increase in atomic number. Samarium, for example, it is like just like steel hard. Okay, they are having typical metallic structure and are good conductors of heat and electricity because that is the common property for metals. Fine. Density and other properties change smoothly except for these two. Remember when we have discussed atomic radius, then for these two elements there was discrepancy. Okay, so density and other properties, there is smooth change except these two elements, and it is because of their fully filled stable configuration 487, 414, and sometimes for samadium and TM also this type of discrepancy is observed. The first ionization enthalpy of these lanthanoids, this is around 600 kilojoule per mole, and the second ionization energy 1200 kilojoule. And obviously the second ionization energy will be high compared to the first one, because when you have already removed one electron, it has +1 oxidation state. Now you are removing the second electron from a positively charged species. So this is really difficult process. So you have to provide more energy. So second ionization energy, that is always higher than the first ionization energy. Here we have two properties, density in the left hand side. So all these, that is this round shape, they are density, and the square shapes, they are melting point. So melting point is present in the other side, right hand side, and this axis, it is having all the atomic numbers. 57 is the atomic number of La and up to lutetium. So see, density, there is gradual increase. These two, there is discrepancy, it is already mentioned here for europium and ytterbium. Similarly, when it is melting point, there is no gradual, that is again at these 2 points you can see there is some discrepancy, but except these two, there is more or less increase. Fine. Now for comparison purpose, we also have mentioned aluminium, because that is also having some metallic character. So the melting point of aluminium is 660 degrees centigrade. So see, this is the line for melting point, because melting point, all these are in degree centigrade. So this is 660, that means somewhere here, just below 700. But for lanthanides, now see, the values are ranging from 1600 up to the minimum one, that is for cerium. This is also even greater than aluminium. So their melting point compared to other metals are very high. And now compare the density. Aluminium is having density in the range 2.7 gram per cc, around here. But for lanthanides, the densities are in this region. See, so densities are also very high. So from these two, you can compare how it is changing. So some more discussion will be there related to lanthanides. So we will finish here. So regarding on the slides in this class, if there is any doubt, please mention. So as there is no doubt, we are ending the session here. Thank you for listening.